The fastest passenger train in the world reached a speed of 374 miles per hour, 602 kilometers per hour, during a test in SC Maglev in Japan in 2015. At that speed, if it were to run on a standard U.S. freight railway, the kind you see carrying coal or grain across the Midwest, it would derail in under a minute. And not just because of the speed, it's because the tracks themselves are built on completely different physical principles. That's exactly what we're about to explore here on Simple Why. High-speed rail as a formal system began operation on October 1, 1964. That was when Japan launched the Shinkansen, known to most Americans as the bullet train. Running between Tokyo and Osaka at 130 miles per hour, or 210 kilometers per hour. At the time, nothing like it existed anywhere in the world. The Japanese government didn't build this railway as a novelty. They built it because conventional rail could no longer move passengers fast enough between the country's two most important economic centers. The existing line was congested, slow, and overloaded with freight traffic. A dedicated system designed for one specific purpose was the only solution that actually worked. Europe followed in the 1980s and 1990s with France's TGV, Germany's ICE, and Spain's AVE. In the United States, Amtrak's Acela service launched in 2000 along the Northeast Corridor and is technically classified as high-speed rail, although it only reaches a maximum of 150 miles per hour, or 241 kilometers per hour, on limited sections of track. Most of its route runs on older, shared infrastructure, and that's exactly why it can't go any faster. When we looked into the minimum speed required to qualify as high-speed rail, the number was lower than expected. The International Union of Railways defines it as 200 kilometers per hour, about 124 miles per hour, on upgraded tracks. On newly built dedicated lines, that threshold increases to 250 kilometers per hour. So technically, Acela meets the standard, but just barely, and only in certain conditions. There's a common belief that high-speed trains can't run on conventional tracks because they're too heavy. You'll hear that repeated a lot, and it sounds reasonable. But according to the Federal Railroad Administration, high-speed trains are actually lighter per car than typical freight equipment. The real limitation is geometry, stability, and precision, not weight. Standard U.S. rail, the kind the industry classifies as Class 1 through Class 5, is built around a simple reality: moving heavy freight slowly. A single freight car can weigh up to 286,000 pounds, or about 130,000 kilograms. The tracks flex, joints shift. Small deviations, sometimes as much as a quarter inch, are completely normal and still fall within federal safety limits. At 60 miles per hour, trains can handle that, but at 180 miles per hour, that same quarter inch becomes a catastrophic force. The physics escalates fast. Vibrations begin to resonate, lateral forces spike, and the contact geometry between wheel and rail starts to lose stability. Federal Railroad Administration track safety standards published under 49 CFR, Part 213, cap the speeds of conventional freight lines far below high-speed thresholds for exactly this reason. Then there's curvature. Most conventional rail lines were surveyed in the 1800s, routed around mountains, rivers, and property boundaries. High-speed rail requires curves engineered with extreme precision, with minimum radii measured in miles, not feet. So how do you actually build a track that a 200-mile-per-hour train can safely run on? It starts with the foundation. High-speed rail typically uses a concrete slab base instead of traditional ballast. Ballast, the crushed stone you see under regular tracks, shifts over time. A concrete slab doesn't. Japan's Shinkansen system relies heavily on slab track across its network, and that's one of the reasons it has maintained such precision for decades. The rails themselves are welded together into what engineers call continuous welded rail, or CWR. No gaps. Just a single, uninterrupted strip of steel that can stretch for miles. Joints are where conventional tracks lose precision and generate vibration. Eliminating them is one of the most important upgrades in high-speed rail design. The sleepers, or ties, are made from pre-stressed concrete instead of wood. Concrete holds its geometry. Wood compresses, twists, and degrades. At high speed, even slight movement in the ties translates directly into movement in the rails, and that leads to instability. Then comes curve engineering. High-speed lines use a feature called super elevation, raising the outer rail higher than the inner, combined with long, gradual transition curves. This keeps lateral forces on both passengers and equipment within safe limits. It's similar to a highway on-ramp, but engineered with millimeter-level precision. And honestly, when you break it down like this, the level of accuracy required at every stage is remarkable. What makes high-speed rail special isn't any single component. It's system-level precision. Every element is engineered to work together. Track geometry is monitored continuously. Japan's Shinkansen uses dedicated inspection trains that run at night, measuring alignment down to extremely small tolerances. Maintenance crews respond to deviations long before passengers ever feel anything. The signaling system is completely different from conventional rail. High-speed trains don't rely on trackside signals. Instead, they use in-cab signaling, where speed limits and track conditions are transmitted directly to onboard computers. This allows safe operation at speeds where a human operator couldn't reliably react to external signals. And the rail corridor itself is fully separated. No level crossings, no pedestrian access. Every intersection is handled by bridges or tunnels. That removes one of the biggest sources of risk that conventional rail still deals with every day. When you put all of this together, high-speed rail stops being just faster trains and becomes an entirely different system. China operates the largest high-speed rail network in the world, over 42,000 kilometers as of 2024, more than the rest of the world combined. That's a scale most Americans don't fully realize. In Spain, the AVE network connects Madrid to Barcelona, about 620 kilometers, in just 2 hours and 30 minutes by rail. When you factor in airport time, a flight often takes longer. Then there's an unexpected use: freight. Japan has experimented with running high-speed freight services on Shinkansen lines during off-peak hours, moving small, high-value goods between cities at bullet train speeds. It sounds unusual, but it's real. In the United States, the Northeast Corridor remains the only region with true high-speed potential. And even there, aging infrastructure limits what's possible. California's high-speed rail project is still under construction as of 2025. Built from the ground up as a dedicated system, the only way to truly make it work. The biggest barrier to high-speed rail in the United States isn't technology, it's land. Building dedicated corridors through dense, privately owned urban areas is extremely expensive and legally slow. The California project has already pushed costs past $100 billion for its initial segments, and it's still years away from carrying passengers. The engineering is solved, the model is proven. The real challenge is infrastructure investment at a scale the US hasn't committed to since the interstate highway system of the 1950s. One direction gaining momentum is the use of electric multiple units, trains where each car has its own motor, replacing traditional locomotive-hauled systems. They accelerate faster, distribute weight more evenly, and are easier to maintain. It's still early in the US, but globally, this is already the standard for modern high-speed systems. So the next time you see a train crossing a bridge or rolling through a freight yard, there's a lot more happening beneath those tracks than you might expect. The gap between conventional rail and high-speed rail isn't just an upgrade. It's an entirely different category of engineering, built from the ground up for a completely different purpose. What surprised you the most? Drop it in the comments. We read all of them. And if there's a topic you want us to explore next, leave it below. If we pick yours, we'll give you a shout out. Subscribe so you don't miss the next one. Thanks for watching Simple Why.